Swayam Prabha. Digital India. Educated India.
Good morning. We continue with our discussion on B-spline segments and curves. Previously, we had discussed the strong convex hull property of B-spline curves to quite some extent. Let's revisit that property. So this is our B-spline segment, P of t, which is defined as summation I going from 0 to n p plus I of t times bi. These are our B-spline basis functions, and these are the design points that you specify. The strong convex hull property would state that the B-spline curve P of t is contained in the convex hull defined by the polyline bj plus 1 up till bj plus p minus 1 for values of t in the interval t j plus p minus 1, t j plus p. And this convex hull is actually a subset of the parent hull defined by all the design points that you specify from b0 to bn. Just in case, if you think you are getting lost in these indices, let me try to explain how this property works on board. Let's try to work with order 5 B-spline basis functions. We have the definition of B-spline curve as b of t, it's a vector, equals summation I going from 0 to n. These are the n plus 1 design points, n p plus I of t times b of I. These are the design points that you have specified. As I said, we are working with p equals 5. Let's have an intermediate knot ti. To the left, ti minus 1, ti minus 2, ti minus 3, ti minus 4, ti minus 5, maybe ti minus 6, and to the right we have ti plus 1, ti plus 2, ti plus 3, ti plus 4, ti plus 5, ti plus 6. This is our parameter axis t. Now let's concentrate on this interval ti plus 1. The first B-spline basis function of order 5 will be standing on 1, 2, 3, 4, 5 knot spans. It will be starting from ti minus 4. I'll have to be careful with the continuity conditions here, and it will be ending at ti plus 1. This is n 5 equals 5 here, remember, I plus 1. The second one, similarly, will be n 5 I plus 2. The third one, n 5 I plus 3. The fourth one, this is n 5 I plus 4. The fifth one, n 5 I plus 5. All these are functions of t. the sixth one, n5 I plus 6 of t, and so on. Now remember, over this interval, ti plus 1, n5 I plus 1, n5 I plus 2, which is this one here, n5 I plus 3, which is this one, n5 I plus 4, and n5 I plus 5. All these 5 basis functions will be non-zero here. Further, n5 I plus 1 of t, n5 I plus 2 of t, n5 I plus 3 of t, n5 I plus 4 of t, and n5 I plus 5 of t, they will sum to 1. So in a sense, in the interval ti plus 1, n5 I plus 1 of t, 2, n5 I plus 5 of t, they will sum to 1. All the other B-spline basis functions over this interval will be 0. Now let's look at this definition of a curve. What is the design point associated with n5 I plus 1? With n5 I plus 5, bi is associated. So let's work backwards. So with this one, bi is associated. With this one here, bi minus 1 is associated. With n5 I plus 3, bi minus 2 is affiliated. With n5 I plus 2, bi minus 3, and with n5 I plus 1, bi minus 4 are associated. Remember, all these are vector design points. For values of t within this interval, ti plus 1, these 5 B-spline basis functions, they are locally barycentric. You would know, in fact, you know what I mean. They all are non-negative and they sum to 1. Because of which, these 5 design points, bi minus 4, bi minus 3, bi minus 2, bi minus 1, and bi form a local convex hull. In a sense, for values of t in between ti and ti plus 1, a part of the segment of bi will be lying within the convex hull defined by these 5 points. Let's continue further. With n5 I plus 6, we have the point bi plus 1 associated with it. The story for the interval ti plus 1, ti plus 2 is identical. Here, we'll have n5 I plus 2, n5 I plus 3, n5 I plus 4, n5 I plus 5, and n5 I plus 6 non-zero, and they would sum to 1. Because of which, the subsequent set of 5 points, p equals 5, the subsequent set of 5 points, which are bi minus 3, bi minus 2, bi minus 1, bi and bi plus 1, they will form a local convex hull. In other words, for values of t in between ti plus 1 and ti plus 2, these 5 points will form a local convex hull, and the segment b of t will have a part of it within the convex hull defined by these 5 points for values of t in this interval. So in case you are getting confused with the indices, it's always a good idea for you to sketch your B-spline basis functions on board or on a piece of paper and try to understand yourself how local barycentricity works. In the previous lecture, we had seen something very similar when we were working with multiple knots. With such an exercise, it becomes a lot easier for us to understand how to design B-spline curves with multiple knots and with multiple control points. For example, if these 5 points coalesce to become a single point, the convex hull would degenerate to a single point itself, and it will force the curve to pass through that point. Or more specifically, for values of t equals ti, n5 I plus 5 of t is 0, as you would notice, and n5 I plus 1, n5 I plus 2, n5 I plus 3, and n5 I plus 4 are non-zero, and they sum to 1. Now, if I coalesce 4 of these points together, that means if bi minus 4 equals bi minus 3 equals bi minus 2, which is equal to bi minus 1, for t equals ti, the curve is bound to pass through this point. You can work out other properties in a very similar manner. This is lecture number 30. Today, we will concentrate specifically on knot vectors, knot vector generation. So, if you are given data points, degree of basis functions, and the knot vector, a B-spline curve can be computed. Now, data points are usually specified by a user, and so is the case with the order or degree of the basis functions, and therefore of the B-spline curve. How about the knot vector? Is it to be specified by the user? Maybe or maybe not. We'll talk about that in today's lecture. One would notice here that we have too much of freedom when designing B-spline curves. As a user, I can freely specify a knot vector. But is it possible for us to avoid knot vector specification? We are specifying anyways too much of information already. If it is possible that we don't specify a knot vector, is it further possible for us to automate knot vector generation? These are the questions that we'll be keeping in mind when discussing concepts in today's lecture. Let's talk about some parameterization schemes. Given a few data points, we can determine some parameter spacing. The interval used may be normalized, and maybe we can extract the knots from this spacing. If we specify n plus 1 data points, this would imply that we might be able to extract n plus 1 parameter values. Of course, this may not be a unique way to determine a knot vector. There could be many other ways of doing that. Let's focus on uniform parameterization now. By uniform, it's essentially implied that parameters at equal spacing can be generated. Let's say we have an interval AB and we would like to equally space n plus 1 parameters in this interval. How do we do this? Well, let's say our parameter values are given by u sub I, and they are equal to a plus I times b minus a over n. Here I is an index going from 0 to n. For I equals 0, I have u of 0 equals a, and for I equals n, these two n's would cancel out. This a would get cancelled out with this minus a, and therefore u of n will be equal to b. All the other parameters are spaced by some length b minus a over n. This is straightforward, but this uniform parameterization scheme does not represent the relative placement of data points. For that, we have the card length parameterization. Here, parameters representing the relative placement of data points can be generated. N plus 1 parameters that we are looking for can be placed proportional to the chord lengths of the control polynomial. Let's work with the example that we have been working so far. Let's say we have a few data points here, B0, B1, B2, B3, B4, B5, B6, 7 of them. Corresponding to the first data point, we have the parameter value u of 0. Corresponding to the second point, B1, we have the parameter value u1, and so on. I can express u1 as u of 0 plus the absolute value or the chord length between these two data points. Absolute value of B1 minus B0. Remember, these data points are vectors, specifically position vectors. How about computing u2? I can compute u2 as u0 plus the absolute value of B1 minus B0 plus the absolute value of B2 minus B1. In a sense, u2 is u0 plus this chord length here plus this chord length here. Now, for u3, we'll be performing the computation in a very similar manner. u3 will be given by u0 plus this chord length plus this chord length plus this chord length. And we can generalize this process. And we can say u of I equals u of 0 plus summation k going from 1 to I of the absolute value of bk minus 1. Here the index I would go from 1 to n. So notice or realize that there are two indices in working here. One is the index k, the other one is the index I. Now, to set the parameterization in AB, we'll have to perform some scaling. We can do the scaling in this manner. U of I equals A plus B minus A times, in the numerator we have summation k equals 1 to I of the absolute value of bk minus 1, and in the denominator we have the index k going from 1 to n in the summation of the absolute value of bk minus 1. So if you notice, this denominator here represents the sum of all the chord lengths. Now notice how the scaling works. Let's say for I equals 0, we are looking at the first parameter value here. For I equals 0, this is equal to 0, for which u of 0 will be equal to a. And for I equals n, the numerator and the denominator are identical. So this fraction will be 1, for which u of n is equal to a plus b minus a, which is b. So all these chord length parameters are now in the interval a and b, but they are not uniform. In fact, they are placed contiguously as per the chord lengths. Centripetal parameterization technique. You're working with the same example. The idea is that the centripetal acceleration should not be too large at sharp turns or the smaller radii of curvature. Now, in the domain given by two values a and b, between the chord length parameterization and centripetal parameterization, this exponent in both the numerator and the denominator is the only difference. So u of I is given by u of I equals a plus b minus a times, in the numerator we have k equals 1 to I summation of the absolute value of bk minus 1 raised to half. So if you notice, we are considering the square root of the chord lengths. In the denominator, we have k equals 1 to n in the summation of the absolute value of bk minus 1 raised to half again. Here the index I is going from 1 to n. Now what I can do is I can combine the uniform parameterization technique, the chord length, as well as the centripetal techniques into a single expression given by ui equals a plus b minus a times summation k going from 1 to I of the absolute value of bk minus 1 raised to e some exponent. I'll talk about that in a while, over summation k going from 1 to n of the absolute value of bk minus 1 raised to e again. The index I, as usual, will go from 1 to n. Now for the exponent e equals 0, we get uniformly spaced parameters. For e equals 1, we achieve the chord length parameterization, and for e equals half, we get centripetal parameterization. Well, I can use e as a free choice. I can specify any value I want for it. It won't make much of a difference in terms of the expression, but yes, it will space out these parameter values in different ways. Now, so far, you would probably not realize the relation between these parameter values u of I and the knot vector or the knots. You might want to be a little patient as of now. We would be able to specify that relation very soon. Coming to knot vector generation. Now, given the number of data points n plus 1, the order of basis splines p, these are the choices that the user would exercise. You would know very well that the number of knots to be used is given by n plus 1, which has to be equal to n plus 1 plus p, the number of design points plus the order of the B-spline curve. We can use n plus 1 parameter values ui that we have seen before to find some or all of the n plus 1 knots ti. This is how these parameters are getting related to the knots. Now, this would depend on the end conditions that you would prefer to choose for any spline at hand. Well, we can talk about unclamped splines, maybe those which are clamped at one end or some which are clamped at both ends. Let's take these cases one by one. Let's consider the unclamped splines first. Here we all know that n plus 1 equals n plus p plus 1 knots are all simple knots. Of these n plus 1 knots, namely Tp, Tp plus 1, Tp plus 2 up till Tn plus p, may be chosen as the parameter values themselves. U of I, where I would go from 0 to n. These U of I can either be uniform or they can be computed using chord length or centripetal parameterization. Well, how about the remaining first p knots? We can choose these knots T0, T1 up till Tp minus 1 freely. The next case is of splines clamped at one end. Well, we have seen before that the knot corresponding to that end must be repeated at least p minus 1 times. Can you guess why this is so? Once again, you will have to use the local barycentricity property for this. For example, if the first end of the spline is clamped, then we have the knots T1 equals T2 equals T3 up till T of p minus 1. And these would be our free choices. Now, the knots Ti plus p can be set to be equal to U of I, that we would have computed using different parameterization schemes we have discussed just now. The index I is going from 0 to n. How about t sub 0? As you would know, this is again a free choice. So we can set t0 equals t1, implying that the first p knots now are equal. It doesn't change things much. We'll still be getting our spline clamped at the first end. Now the case with the last end clamped. Well, here we can have the first n plus 1 knots as ti equals ui. And then we can set tn plus 1 equals tn plus 2 equals tn plus 3 up till tn plus p. How many are these? There are p of them, and there are free choices for us. Now this one could be a tricky one. Splines clamped at both ends. Now notice that the knots Tp minus 1 and Tm minus p plus 1, which are the limits of the full support range, may each be repeated p times. This would mean that T0 equals T1 equals T2 up till Tp minus 1. So these are the first p knots which are equal, and Tn plus 1 equals Tn plus 2 equals Tn plus 3 up till Tn plus p. These are the last p knots which are equal. Note that n will be equal to m minus p. Okay, so here we have determined p plus p, 2p knots in total. So this would correspond to a free choice for me, and again this would correspond to another free choice. How about the rest of the knots? They will be the remaining n minus p plus 1 internal knots given by Tp, Tp plus 1, Tp plus 2 up till T sub n. And these can be determined as follows. They can be either evenly spaced in the interval AB, which would mean that the first p knots T0, T1, T2 up till Tp minus 1 equals A, and the intermediate knots given by Tj plus p minus 1 can be computed as A plus b minus A times j over n minus p plus 2. Here the index j is going from 1, 2, 3 up till n minus p plus 1. And the last p knots, which are Tn plus 1, Tn plus 2, Tn plus 3 up till Tn plus p, they can all be set to B. Let's try to visualize what's happening here. So we have the parameter axis here, and we are trying to fit n plus 1 equals n plus 1 plus p knots within the interval given by AB. We are working with splines clamped at both ends. Now, what we have done is we have repeated the knot here p times, and we have repeated the knot here p times as well. So we have said that T0 equals T1 equals up till Tp minus 1. They are all equal to the value A, and Tn plus 1 equals Tn plus 2 equals Tn plus P. They are all equal to the value B. What remains is n plus 1 plus p minus 2p, which is n plus 1 minus p knots that we need to determine within this interval. So with the evenly spaced scheme, we are saying that these intermediate knots, they are placed as p minus a times j over n plus 2 minus p. We'll have something here. We'll worry about that later. Here j is going from 1 up till n plus 1 minus p. Now we have to determine the knots starting from Tp and ending at Tn. What would be the index corresponding to this T? And how will this index be related to J? Clearly, this is P plus J minus 1. When J equals 1, we get to specify the next knot T sub P, and when J equals n plus 1 minus P, the last knot becomes T sub P plus n plus 1 minus P minus 1, which is Tn right here. What did I miss here? I missed this term. So this would be my knot Tp corresponding to j equals 1. This is Tp plus 1 for j equals 2, Tp plus 2 for j equals 3, up till Tn for j equals n plus 1 minus p. Now notice that these knot spans will be of equal length. Now realize that this scheme here did not use the knowledge of the position of control points, and it was relatively simple for us to generate the intermediate knots between the interval or within the interval AB. Now if we need to use the parameterization schemes like the chord length parameterization or the centripetal parameterization, we will have to modify the scheme a little bit. We can think of computing the internal knots by averaging a few parameters. This could be one of the candidate schemes. So the internal knots T j plus p minus 1 can be equal to 1 over p minus 1 summation I going from j to j plus p minus 2 of u sub I. These are the parameters we have extracted via the chord length or centripetal parameterization. Here again, T0, T1 up till Tp minus 1, they are all equal to A, and Tn plus 1, Tn plus 2, Tn plus 3 up till Tn plus P are all equal to B. Now what's happening here? So say we have parameters u0, u1, u2, u3, u4, and so on up till un. I may have generated these parameters using either chord length parameterization or centripetal parameterization, or using the general scheme that we have discussed before for any value of E. Let me jot down a few more parameter values and so on. Now this value would correspond to the design point B0, this one corresponding to B1, this one B2, B3, B4, and so on up till un, which would correspond to the last design point Bn. They are all vectors. But note that these values u0, u1, u2 up till un, they are all scalars. Now by this time I have determined my first P knots. Also, I have determined my last P knots. Say they are equal to A, and here all these are equal to B. I have to compute my internal knots Tp, Tp plus 1, Tp plus 2, and so on up till Tn in such a way that I can use these parameter values that I have generated from before. Now to compute Tp, I can think of choosing the p minus 1 parameter values starting from u sub 1. So I'll have to choose u1, u2, u3 up till u p minus 1. So if p is 4, the last parameter value that I choose will be u of 3. Anyhow, the idea is to choose p minus 1 of these parameter values and average them out. Let's say if p equals 4 in our case, then we'll have to be choosing p minus 1 equals 3 parameter values at a time and averaging them out. So for instance, Tp would be the average of u1, u2 and u3. Tp plus 1 will be the average of u2, u3 and u4. Tp plus 2 will be the average of u3, u4, u5 and so on. Notice that I have not used the first parameter value u0. I have started from the second parameter value. How about for Tn? For p equals 4, let's say I don't use u of n. Instead, I use un minus 1, un minus 2 and un minus 3. So to compute Tn, I'll simply be performing the average of these 3 parameter values. With the first p naughts as a and say a is equal to u sub 0, with the last p naughts as b and we set un equals b, my internal knots Tp, Tp plus 1, Tp plus 2 up till Tn can be computed as averages of these parameter values. Let's verify if this is really the case. Let's say for the first value of j equals 1, we have in the summation I going from 1 up till p minus 1. U of I, this index I will be going from 1 to p minus 1. For j equals 1, we are computing t sub p. So in a sense, t sub p is the average of the first p minus 1 knots. Of course, we are ignoring the value u sub 0 here. How about for j equals 2? I goes from 2 to p, again p minus 1 parameters, and these parameters will be from u2 to up, again p minus 1 of them, and so on. So in summary, Tp is the average of u1, u2 up till up minus 1. Tp plus 1 is the average of u2, u3 up till up, and so on. Let me summarize now. As a user, you will have to specify, say, n plus 1 design points. You'll have to specify the order of the B-spline curve, and then once you know the number of knots, you can use the techniques that we have discussed today to generate those knots. Depending on different cases of B-spline curves you are thinking of. They could be simple B-spline curves, that means unclamped, or you can clamp a spline at one of the ends or maybe at both ends. Accordingly, you can think of generating the knots using different schemes that we have discussed today.